The man known to history as Albert Einstein was born on the 14th of March 1879 in the city of Ulm, in the south of what was then the German Empire. Ulm was a major urban centre of the Kingdom of Württemberg, a major constituent part of the German state in the late 19th century. His father was Hermann Einstein, an Ashkenazi Jew from Buchau in Württemberg. Hermann had been academically gifted and showed a strong ability in the field of applied mathematics when studying in Stuttgart, the capital of Württemberg, in his youth. However, the Einstein family were not wealthy, and he was forced to abandon his studies and went to work in the feather bed shop run by his cousins, Moses and Hermann Levy, in Ulm in the 1870s. Albert's mother was Pauline Koch, a member of a family of German Jews who had developed extensive connections as purveyors and merchants in Württemberg. She married Hermann Einstein in 1876, and Albert was their first child. A daughter, Maya or Maria Einstein, was born 2 years later, in 1881. Albert's youth was dictated to a considerable extent by his father's business dealings. When he was still an infant, Hermann Einstein, following the business advice of his brother Jakob, decided to move the family to Munich, the largest city in southern Germany, lying some 170 kilometers to the east of Ulm. This occurred in 1880, as Jakob and Hermann sought to establish Einstein & Co. as an electrical engineering company in Munich, just as the great age of electrification was about to begin sweeping the Western world. There, Albert was enrolled in a Catholic elementary school, before being transferred to the Luitpold Gymnasium in Munich in 1887. Albert remained there until 1894, but at that stage the Einsteins were once again uprooted when Hermann and Jakob failed to secure a contract to begin the electrification of Munich. Instead, they headed for northern Italy, settling first in Milan and then in Pavia. Albert briefly remained in Munich to continue his studies, but after several months became disillusioned with the strict rote learning on offer at the gymnasium and convinced both his parents and the school authorities to let him leave to join them in Italy. Albert continued his education in Italy from 1894 onwards. He was already showing distinct signs of a precocious ability as a scientist and mathematician, although his father desired for him to take a more keen interest in applied engineering and so follow him into the family business. In Munich in the summer of 1891, he had taught himself algebra and the advanced geometry of the ancient Greek mathematician Euclid. A family tutor by the name of Max Talmud, who excelled himself in the fields of optometry and ophthalmology, was employed by the Einsteins to teach young Albert advanced mathematics and scientific principles, but he soon found his charge was becoming more knowledgeable than he himself was when it came to subjects such as calculus, algebra, and geometry. Nor was he a prodigy who was solely interested in scientific and mathematical topics. As he entered his teenage years, he was also reading widely of some of the most advanced philosophical writers of the 18th and 19th centuries, notably the German Enlightenment philosopher Immanuel Kant. Kant's Critique of Pure Reason, first published in 1781, and offering one of the most analytical discussions of metaphysics, the study of the nature of reality, is one of the densest philosophical tracts ever written. Yet Albert seemed to understand it clearly at age 14, something which bewildered his tutor. Young Einstein's abilities did not go unnoticed by his teachers, tutor, and parents. Thus, shortly after he arrived in Pavia, and following his 16th birthday, he was sent to take the entrance exams at the Swiss Federal Polytechnic School in the city of Zurich, an advanced school of science, mathematics, and engineering. Although he scored high on the technical exams, Albert was not admitted at this time, in part owing to his youth. The following year, he passed the Swiss Matura, an equivalency exam in the country for those who had not gone through the formal schooling process within Switzerland, but wished to complete the secondary education curriculum there. Earlier that year, he had also renounced his German citizenship to avoid being called up for the required military service expected of all young men in the country. Thus it was that as a stateless individual, he finally entered the Polytechnic School in Zurich in the autumn of 1896, age 17. There he would study physics and mathematics, the two subjects which he had demonstrated a prodigious ability in since he was a child. He would remain there for 4 years, eventually acquiring a diploma in 1900. Einstein's years in Zurich were those in which his research interests began to emerge in a fully formed state. He was becoming an eclectic scientist, one who might broadly be categorized as a physicist, but whose area of expertise covered a wide range of topics, such as the discovery of an accurate way to measure the dimensions of tiny molecules, a field of endeavor belonging to quantum mechanics, the broad science of describing the physical properties of nature at the atomic and subatomic level. Additionally, he was concerned to measure how light moves. At the time he was beginning to conduct complex research into this subject in turn-of-the-century Zurich, the prevailing view amongst European and North American scientists was that light traveled exclusively in wave patterns. As would become clear in the years that followed, Einstein doubted this theory and believed a further layer of complexity existed within the mechanism whereby light traveled. These and other aspects of advanced physics were at the heart of Einstein's research in his mid-20s. They formed the core of his doctoral thesis, which he was studying for part-time throughout the early 1900s and which he completed in 1905 in Zurich, entitled A New Determination of Molecular Dimensions. His research in the early 1900s was evidently aided by Mileva Marić, a young Serbian mathematician and physicist who had begun attending the Polytechnic School in Zurich around the same time that Einstein had first been granted teaching hours there after finishing top of the class in 1899. Marić was one of only 2 female students attending there at the time. She and Einstein were soon involved in a relationship with each other, and it is now assumed that she contributed to his research, though the exact degree to which she did so is unclear. In any event, her own research was interrupted in the summer of 1901 when she fell pregnant. Marić and Einstein were not yet married by then, and this was a time when having a child out of wedlock was still considered a social scandal. It appears that Mileva returned to her native Serbia to have the child, who was called Liesl in their correspondence after her birth. What happened to her thereafter is unclear. Some sources believe she died from scarlet fever in 1903, but others suggest she was put up for adoption in Serbia. It seems more likely that she died as Marić and Einstein had married in January 1903. They would go on to have 2 further children, a boy, Hans Albert, born in the summer of 1904, and another son, Eduard, in 1910. It may seem peculiar in retrospect, but Albert did not immediately find it easy to find a teaching position upon completing his diploma in Zurich in 1900. He spent the next year and a half trying in vain to acquire a junior-level lecturing and research position in a Central European university, but to no avail. In the meantime, he acquired Swiss citizenship in 1901, finally acquiring statehood after half a decade of theoretically being without a national affiliation. With Swiss citizenship in hand, a family friend and associate from the Polytechnic in Zurich, Max Grossmann, enlisted the aid of his father to get Einstein a post at the Swiss Patent Office in the capital Bern. Here Einstein worked as a patent assistant examiner. What this effectively meant was that Albert was tasked with assessing the merits of various inventions and devices, which were brought before the patent office by individuals who wanted to have their intellectual ownership of their invention recognized. To ensure credit for the device was given to them, and they could benefit financially. Einstein worked there for the next several years. Beyond serving to support his young family, his work focused on many different devices involving electrical conduction and mechanics, and it has been posited that this impacted on Einstein's own research during his formative years. The manner in which Einstein burst forth from almost complete obscurity within the developed world's scientific community to become one of Europe's paramount physicists in the mid-1900s is one of the strangest stories in the history of science. While he was completing his doctoral studies and working in the patent office in Bern in the first half of the 1900s, Einstein was working on a series of papers for publication in the pages of Annalen der Physik, one of the world's leading academic journals for the study of physics, which had been published in Germany from 1799 onwards. This eventually resulted in 4 separate research papers, which were all published in the journal in 1905. Individually, they made major contributions to various fields within the study of physics. Collectively, they have been deemed to represent a revolutionizing of humanity's conception of the molecular and atomic dimensions of the natural world and the development of modern physics. Consequently, 1905 is usually referred to by biographers of Einstein and historians of Western science as the Annus Mirabilis, or miracle year, of Einstein's career. The first of Einstein's 4 papers of 1905 was entitled On a Heuristic Viewpoint Concerning the Production and Transformation of Light, and was published on the 9th of June. This explained what is known as the photoelectric effect for the first time. The photoelectric effect is where electrons are emitted when electromagnetic radiation, such as light, hits off a material or substance. The electrons which are emitted during such a process are called photoelectrons. Up until 1905, when Einstein described this photoelectric effect, the prevailing view amongst physicists was that light traveled much like a wave in the ocean. But Einstein explained that the photoelectric effect meant that light also traveled in what he termed to be a finite number of energy quanta, which moved without dividing, and which could only be absorbed or generated as entities. This not only explained much that was previously unknown about the nature of light and electrons, but had fundamental implications for understanding how light of a certain frequency could bring sufficient energy into play to liberate an electron. This built on work conducted by physicists such as Max Planck in previous years, but Einstein's paper added extensive new details on how energy and light interacted through the photoelectric effect. This had major implications for practical applied physics, and many years later, this discovery would be directly cited when Einstein was awarded the Nobel Prize for Physics, although it was not until the mid-1920s that his findings were fully accepted amongst physicists. Just 6 weeks after this first paper appeared, Einstein's second paper of 1905, entitled On the Motion of Small Particles Suspended in a Stationary Liquid, as Required by the Molecular Kinetic Theory of Heat, was published in Annalen der Physik on the 18th of July. Prior to Einstein's paper, there was no accurate way of measuring the dimensions of molecules, but several scientists in the 19th century, such as John Dalton, had noted that chemical substances tended to combine together or break down in weighted proportions, which suggested that they were all made from an as yet unidentified physical molecule that was common to all things. These unitary molecules are known as atoms today, after a word which had been coined by ancient Greek philosophers of the 6th century BC, who were themselves seeking to understand the nature of existence 2.5 millennia before Einstein's time. Einstein's second 1905 paper showed how these atoms could be measured more comprehensively by using what was termed Brownian motion, whereby particles, in this case pollen, were suspended in a water solution. Einstein's paper, along with a corroborating study produced by the French physicist Jean Perrin in 1908, demonstrated unequivocally that atoms and molecules were real entities, which were the building blocks of existence. Thus, this second paper of 1905 was a major contribution to humanity's acceptance of the existence of atoms and molecules, and the emergence of atomic theory as the basis of much of 20th century physics. Einstein's third paper was published just over 2 months later on the 26th of September 1905. This was entitled On the Electrodynamics of Moving Bodies and focused on the issue of special relativity. This sought to reconcile an equation which the Scottish mathematician and scientist James Clerk Maxwell had devised in the early 1860s regarding electricity and magnetism. Maxwell's equations led to difficulties in how physicists should understand mechanics which occurred close to the speed of light. In response to this problem, Einstein outlined his special theory of relativity, or special relativity, in his 1905 paper. This stated that the speed of light is the same for all observers regardless of the motion of the light source or the observer of the light source. This opposed the idea postulated over 2 centuries earlier by Isaac Newton, which held that the speed of light is not fixed. Moreover, Einstein's special theory of relativity correctly assumed that when 2 objects are involved concerning light, there is no true way of knowing which is in motion and which is not. Einstein had come to this realization while traveling in a streetcar in Bern in the early summer of 1905 and looking at the clock tower in the center of the city. He realized that if his car suddenly started traveling at the speed of light, the clock arms on the clock tower would suddenly appear as though they had stopped. But the clock inside the streetcar would continue to move around as though nothing had happened, because both Einstein and the clock in the streetcar were traveling at the same velocity. Therefore, the speed of movement was relative. If the streetcar had suddenly accelerated to the speed of light, it would not mean that the clock tower had stopped, only that it appeared to have done so relative to the speed which the streetcar was now traveling at. This was the special theory of relativity at work. Einstein's 4th and final paper of his Annus Mirabilis was published on the 21st of November and was entitled, "Does the inertia of a body depend upon its energy context?" Few have heard of that title today, but a great many are familiar with the equation which Einstein pioneered in the paper, E equals mc squared. In brief, what this means is that the energy of a body at rest, defined as E, is equal to its mass, or m, multiplied by the speed of light, the c of the equation, squared. This equivalency equation showed that a massive particle possesses an energy, or rest energy, which is distinct from the kinetic energy of a particle. This would come to be known as the mass-energy equivalence, and highlights how the rest energy of a particle, such as the nucleus of an atom, could be so massive as to result in an enormous amount of light and thermal energy being released if the particle was disturbed sufficiently. As we will see, the practical application of this equation was to have devastating consequences in later decades, and Einstein later grew to regret this aspect of his research. Einstein's 4 papers published during 1905 did not simply constitute breakthroughs in the confined world of academic theoretical physics. His research shaped the application of science to the modern world in the decades that followed. For instance, when you walk up to an automatic door today and it opens in front of you, this is because the sensors used in the doorway react when the photons in the light beams they emit are obstructed, in this case by a moving person. The sensor then tells the door to open. Einstein first explained how photons work. Solar-powered calculators and street lights that automatically turn on when it gets dark, amongst other innovations, also emerged from his work on light. The special theory of relativity helped lead to the development of global positioning systems, or GPS, over time. Thus, when you switch on Google Maps, it is effectively functioning based partly on research which Einstein published in his Annus Mirabilis papers. And when a nuclear power plant creates massive amounts of energy by harnessing the energy in the nucleus of an atom, they are doing so based on Einstein's discoveries concerning energy and mass equivalence as contained in the equation E equals mc squared. Einstein's groundbreaking research findings, published in 1905, soon came to the attention of the European scientific community. Though at a time when people were still reliant on the circulation of hard copies of academic journals and word of mouth for research to be disseminated, it took a few years for the import of his findings to become clear across Europe. As they did, they transformed his career. By 1908, he gained a teaching post at the University of Bern and was able to leave his position at the patent office. The following year, he was appointed to a new chair of theoretical physics, which had been created at the University of Zurich. He remained there for the next 2 years. During this time, he continued to refine some of the points he had made in his 1905 papers, while also moving on to begin developing the theory of general relativity as an offshoot of his work on special relativity. The theory of general relativity holds that the observable gravitational attraction between two masses results from the warping of space-time by those two masses. This research made major initial contributions to the science of black holes and other mass objects within the universe.